Welcome to The Explainer. Right at this very second, thousands of human-made objects are just hurtling through a deadly vacuum at 17,000 miles per hour, and they're functioning flawlessly. Today, we're going to decode the extreme engineering behind spacecraft architecture. We're stepping right past those spectacular, fiery rocket launches to look at the invisible, meticulous framework that actually makes all this space exploration possible.
Let's be real. Space is an impossibly hostile environment. There's no air, the temperatures swing wildly, and radiation is constantly bombarding literally everything. Plus, there's the most terrifying constraint of all. Once it's up there, you can't exactly send a mechanic up with a wrench to fix a loose bolt or a fried motherboard, right? Yet, we routinely design these incredibly complex machines that not only survive, but actually thrive up there. So how do we pull that off? Well, it's not magic. It's a rigorous, often completely unforgiving discipline we call systems engineering.
To really get how this works, we have to zoom in on how these massive systems are actually designed and managed on the ground. Picture a giant communications satellite in orbit. It's a total masterpiece of integrated tech, where thousands of individual components have to work in absolute perfect harmony. In a setup this deeply intertwined, a single point of failure, like, a jammed valve, a blown fuse, even just one miscalculated line of code can literally doom a billion-dollar mission. Building something that complex, it requires a completely different way of thinking.
So here's how we're going to break down this beast of a topic today, mirroring the exact top-down approach that systems engineers use in the real world. We'll start with the big space picture, move into the anatomy of a spacecraft, look at surviving the extreme environment, figure out how teams manage all this engineering complexity, and then wrap up with the delicate art of trade-offs. Section 1. The big space picture. Let's kick things off with the macro view to completely redefine what a space mission actually is.
See, there's a really vital distinction between a spacecraft and a space system. A spacecraft is just the physical vehicle, right? The metal, the solar panels, the flight computers out there in the void. But the space system, that's the whole shebang, the entire supporting infrastructure. It includes the launch segment that actually gets it up there, the ground stations with those massive antennas talking to it, and the operations segment, the actual human teams and software running the day-to-day mission. These terrestrial elements are just as critical as the hardware floating in space. Think about it. If a storm takes out your primary ground station antenna here on Earth, your flawless billion-dollar spacecraft suddenly becomes a silent, uncontrollable piece of space debris. The system really is only as strong as its weakest link back on the ground.
Depending on the mission, these systems are deployed into very specific orbits, and those orbits totally dictate the entire engineering approach. A satellite in low Earth orbit, or LEO, isn't just hanging out at a lower altitude. It's experiencing severe thermal shock. Traveling around the Earth every 90 minutes means plunging in and out of darkness thousands of times a year. That requires incredibly robust batteries and thermal materials that can handle constant, brutal expansion and contraction. But if you go further out to medium Earth orbit where GPS lives, or way out to geostationary Earth orbit, GEO, the thermal cycles are way fewer. The trade-off? The spacecraft gets slammed by much harsher, punishing radiation belts. Every single orbit presents a completely different puzzle, heavily dictating the technology that you and I rely on every single day.
Section 2. Anatomy of a spacecraft. Now let's zoom right in on the physical spacecraft itself to check out its internal anatomy.
Pretty much every spacecraft is fundamentally split into two distinct halves, the payload and the bus. The payload is the whole reason we're there. Think of the James Webb Space Telescope. Those absolutely magnificent golden mirrors and ultra-sensitive infrared sensors, that's the payload. It's the star of the show. But those mirrors cannot survive on their own. They are totally dependent on the unglamorous satellite bus underneath them, which provides all the critical infrastructure to keep that payload alive, powered up, and pointed in the exact right direction.
Honestly, it helps to think of these bus subsystems like a living, breathing organism. Command and data handling, that's the brain, constantly processing info and firing off commands. The structure is the skeleton, holding the whole thing together so it survives the unimaginably violent shaking of launch. Power is the cardiovascular system, pumping essential energy from the solar arrays straight into the batteries. Thermal control is basically the sweating and shivering mechanism. It uses complex networks of radiators and heat pipes to dump excess heat out into deep space. And then you have the Attitude and Orbit Control System, or ADCS. That's the inner ear, using star trackers and spinning reaction wheels to maintain perfect balance and orientation when you're completely weightless. Section 3. Surviving the extreme environment. Before we look at how engineers manage all these different organs, we gotta understand the ultimate problem they're solving, the space environment itself.
Every single one of these extreme threats is actively trying to destroy the spacecraft the second it leaves our atmosphere. Take the vacuum of space, for example. It means there's no air for convection, so if your coffee gets cold on Earth, you can just microwave it. But in space, heat has nowhere to naturally dissipate into the air around it. Engineers actually have to actively radiate heat away. Then there are the temperatures. They can swing from a blistering plus 200 degrees Celsius in direct sunlight to a bone-chilling minus 200 degrees the second you hit a shadow. Then you've got radiation, which relentlessly degrades electronics, literally flipping ones and zeros in code and shorting out circuits. That forces engineers to use specialized radiation-hardened components. And don't even get me started on microgravity. It completely upends standard physics, especially fluid dynamics. You can't just rely on gravity to pull your rocket fuel down into the engine anymore. You actually have to use pressurized helium gas or these complex, squeezing bladders to force propellants exactly where they need to go. Every single one of these threats requires a heavy, expensive, highly dedicated engineering solution.
Section 4. Managing engineering complexity. So to combat this impossible environment with thousands of interconnected parts, human teams use the ultimate superpower of systems engineering, decomposition.
In systems engineering, there is this golden rule. The PBS defines what needs to be built, while the WBS defines how the work will be executed to deliver it. It might sound like alphabet soup right now, but this concept is the ultimate blueprint for keeping a massive, multi-year spacecraft project from spiraling into total chaos.
Let's put it this way. If you were building a skyscraper, the PBS, or product breakdown structure, is the literal steel, the glass, and the concrete. It isolates the physical hardware, the solar panels, the reaction wheels, those expensive titanium bolts. But, as we know, hardware doesn't just build itself. That's where the WBS, or work breakdown structure, comes in. Back to our skyscraper analogy, the WBS is the hiring of the welders, the scheduling of the safety inspections, the management of the supply chain. In space systems, the WBS takes that physical hardware and maps out the human element. It covers the environmental testing, the software integration, and the incredibly rigid quality control tasks required to actually bring this machine to life. You absolutely cannot have a functional spacecraft without both of these flawlessly aligning.
But here's the catch. Breaking things down into isolated teams creates a new, kind of dangerous problem known as the price of reductionism. When you divide a system up, you now have to carefully manage the physical and digital interfaces between all those different teams. Imagine being in a weekly engineering meeting, right? The payload team decides, hey, we want a stronger radar instrument. Okay, well that requires more electricity, so the power team now has to add larger batteries. But heavier batteries mean the structures team has to reinforce the chassis to handle the extra launch weight, which means the propulsion team now needs more fuel to push all this extra mass around. It's this crazy cascading domino effect of compromise. You have to rigorously verify that when all these separately engineered pieces are finally bolted together, they don't just break each other.
Section 5. The Art of Trade-offs. And that leads us right to the climax of the engineering process, where the truly painful decisions have to be made.
Here's the harsh truth. You cannot have a perfect spacecraft. You can only have an optimized one. This means you are constantly trading competing factors against one another. Want a massive, high-capability telescope payload? Cool, but your launch costs are going to absolutely skyrocket because of the extra mass. Want to fly in low Earth orbit to get the absolute sharpest pictures of the ground? Well, the atmospheric drag down there is going to shorten your mission's lifespan to just a few years. Do you push for cutting-edge innovation, or do you stick to heavy, proven, reliable heritage parts? Actually, this is exactly why space agencies will often fly computer chips that are literally 10 or 15 years out of date. To an engineer, a slow, outdated chip that is mathematically guaranteed to survive deep space radiation is infinitely better than a lightning-fast modern chip that just dies on day 2. Every single gram of mass, every watt of power, and every dollar of the budget is fought over tooth and nail in these design trade-offs.
When you are building a machine for the void, there is absolutely no room for guesswork. Systems engineering is really the art of balancing the immutable laws of physics against the very real limits of human capability and budget. So the next time you look up and spot a satellite drifting silently across the night sky, ask yourself, what invisible compromises is it carrying through the dark to make that mission possible? Thank you for joining me on this explainer. Until next time, keep questioning how it all works.